All right, so on Friday, we left off, we had, I won't fill in all the numbers and details with our transshipment problem that we have developed here, but what we asked is, what happens if we add this new potential route into our transshipment? How do we handle that? Do you guys remember? I know it was a weekend. So what did we say we were going to do to be able to handle this connection between our producer and our consumer without going through the intermediate distribution channel right here? What did we say we were going to do?
Shift it over.
Shift it over in what way?
Over into the middle.
Okay.
And then have the cost shift itself from 0.
Right, so we were just going to basically have kind of like a virtual entity here, right? So let's go ahead and do that. So now what we need to do is Nebraska and Colorado, let's add a new column. Oops. We're going to add a new location that Nebraska and Colorado can ship to, and that's St. Louis here. So this is, again, how much we do. So that's a variable, so we're not going to touch that. Let's go ahead and move this over. But this is what was that original value supposed to be? From Nebraska to Des Moines, 12. Right, so St. Louis, we have Nebraska here and we have Colorado here, and so there is no connection between Nebraska and this virtual St. Louis center. So what are we going to do? We're going to give it one of those high valued, we can do 1,000, we can do 10,000, whatever, that represents there is no connection. Just so it's easier to do. And then we said that this cost was $13 per 1,000 bushels or whatever. All right, so we've got this new pseudo distribution center, that being St. Louis, that we allow Colorado to ship to, but we don't allow Nebraska to ship to it, but we just give it such a high cost that it's never ever going to choose to use that location. And that means then, let's go ahead and that now we also need, since we had 4 locations that we shipped to, we need 4 locations that we can ship out of right here. So we're going to add, I'll just turn that off real quick. There we go. Turn that off. All right, so now we've got our St. Louis is not just a final destination, but it's that pseudo location. And what should we do? What should we do for the cost here? What's the cost to ship from St. Louis to Chicago? Why? Right, there's no connection between these two, right? So we want to make it so that it's not going to choose that. How much should the cost between St. Louis and St. Louis be? 0, right? We don't want it to cost anything. It's just it's a virtual distribution center. It doesn't cost anything to get it to that final location. And then the cost for the St. Louis to the Cincinnati goes back to 1,000 here, right? Because there is no connection between St. Louis and Cincinnati here. It's only connecting between this virtual center and itself right here. Okay? So then that allows for our new shipping costs, $13 between Colorado and St. Louis, nothing between St. Louis and itself, and we eliminate all other possible shipping lanes that go to or from St. Louis. The other thing we said that we had available to us is we only were going to allow 40 of these units to travel on this, that you couldn't put unlimited amount in there. We said that represented maybe you had a special contract with a transportation company, and that's all the capacity that they had available to them. So where would that show up in this model right here? Where would those 40 units show up? If we were that we need to make sure we put the constraint around those 40 units. You can give me a cell number here. Which cell are those 40 units going to appear in? Yeah. E3. E3, so that would be here, right? Because that's going from Colorado to St. Louis. And so we need to add another constraint to this cell right here that says this value, this individual value right here, has to be less than or equal to 40. Right? We don't have to send 40 units here if we don't want. So that's why it should be a less than or equal rather than an equal. So let's go ahead and finish putting updating our model here. Okay, our objective cell is still correct, B16. Our variable cells, let's see if they're correct. No, because we added rows and columns, right? So let's go ahead and set that up. All right, so now we've got the new St. Louis cells that we added as variables. And then our constraints. Let's check this one first. This is our supply constraints. So that's good, right? The supply and the amount that we shipped should be the same. These are our demand constraints, and that's good. What we demand is what we should receive. And then these right here, yes, let's go ahead and cancel out of here for a second so we can see it all. Okay. In constraint 3.
I think you're doing 3 versus 4.
It expanded one but not the other.
Yeah.
That's nice. All right. So we needed to expand that constraint right there. This is the no net accumulation, right? In other words, everything that comes into a distribution center, which is this amount right here, needs to be everything that leaves the distribution center, which is this amount right here. Yes?
Do we need to move the 100 and the P column up 1?
No, because that's should be, that was just copied value, I think. And so it will recompute it, should recompute it. Okay? But what I want to do is I want to make sure that these equations are still right. Okay? Because we did add some rows, and the equations might not be accurate. So is this accurate? The amount that's shipped out of Nebraska is B2 through D2. No, what should it be? It should be 2 through E2. All right. And the same should be true here. The amount that's shipped out of Colorado is B3 through E3. So we need to update this equation that computed how much was shipped out. Otherwise, we would have allowed any amount to be shipped out of St. Louis and wouldn't have counted it against us. We got free product that we didn't, that we get shipped for. And the same should be true here. That's fine. B2 and C2, D2. But we don't have any coming out of here, right? Let's look at here. K2 through M2. Does that look good? K2 through M2. That's these three columns right here. That's good. K3 through M3. But we don't have anything for Des Moines anymore. And there we go. And we had to add the new one into St. Louis right here. All right? Let's check the demand and received. Is that right? K2 through K4? What should it be? We need to include St. Louis, right? And the same is true in each of these as well.
Doesn't
Okay.
look like it copied 5. But it's still 4.
I must not have hit return yet. Stay. Fine. Type 2. Thank you, Daniel. All right. So let's go ahead and solve this now. Something's wrong there.
Don't you have to say E3 should be less than or equal to 40?
Well, it's definitely less than 40. I do, thank you.
It's the shipped column, it looks like.
So let's add that constraint and then debug this. So E3 should be less than or equal to 40. I don't know what the problem is. We didn't change our shipping costs. Right, we didn't include the St. Louis. Okay, so this should be B2 through D4. Oh, no. E3. Right, so now we've included the St. Louis in the cost. And then this should be K2 through M5, right? And M14. So now what I did is I expanded this one further to include these new St. Louis ones, and I expanded this one further to include St. Louis. And I expanded these down to include St. Louis, and these down, so I included St. Louis right here. Right, so let's see if that helps. No. What's the problem?
I think there's an error in the H column.
I didn't get those updates, did it? Thank you, Daniel. You're really helping me debug these today. There we go. Okay. It matters to get that right. So we actually do send those 40 units. Instead of going through Nebraska to Des Moines, we end up sending them through directly to St. Louis. Or Colorado to St. Louis. All right? So questions about how we did this? the key thing I want you to see is this idea that we have this value right here, that it's theoretically a link. You know, we could ship something from Nebraska to St. Louis according to the model that we've made. It's just it would be a really, really expensive shipment. Okay? And the same is true for shipping between St. Louis and Chicago and St. Louis and Cincinnati. As far as our model is concerned, those are actual links. We have actually gone ahead and made a link here that it costs $1,000. And we've made a link here that costs $1,000 and a link here that costs $1,000, specifically in these directions right here. Okay, so technically, what we put in our spreadsheet was not exactly what we had on the board until I added those 3 links there. But functionally, they did the same thing because we made these costs so high that the program would never end up putting something on those fictitious links. Okay? And the reason why I wanted to highlight that is I'm going to go ahead and go to a new spreadsheet here, is one way that we can think about this instead of having the multiple sets of tables here, is that we can have one single table that represents all the possible links and all the possible costs. So we just would be, instead of 4 tables like we had on the previous, we could have 2 tables, one for the amount shipped and the other for the shipping costs. So you could have, for instance, Nebraska and Colorado and Des Moines, and I'm running out of names here, St. Louis, and Omaha, thank you, and so on, right? And you could do the same thing across the top. Nebraska, Colorado, Des Moines, St. Louis, Omaha. And then you could just put in here what the costs are to go from any of these. So what would the cost be from Nebraska to Nebraska?
0.
Wrong.
What?
In this case, we don't want to ship from Nebraska to Nebraska, right? Because then it would stay in Nebraska. Okay, so this is a little different than having this virtual distribution center that we did here, because this is representing 2 different things. We didn't have a virtual Nebraska. We don't want to ship from Nebraska to Nebraska here. And, of course, Nebraska to Colorado, that's the easier one. I'm sure you are all going to say 1,000 for that as well. And then we can now put in the values that we wanted here, right? What was the value for Nebraska to Des Moines? I could look that up. Right, that would be our 12 right here, right? And we could keep entering these. And now we would only have one table that represented the cost. There would be a lot of 1,000s in this table, right? Because there's a lot of possible links between our different locations and what are actual links. And so all the non-existent links would have to have this 1,000 here. Okay? The nice thing about this is it allows us to have a more generic structure where you could actually have not just 3 layers like we've had here, layer 1, layer 2, layer 3. You could have multiple layers. You could have distribution centers on the West Coast and on the East Coast. You could have things where this distribution center has an agreement with this other distribution center, and there's a connection between them, but there aren't between most other distribution centers. It allows you to have a fully general representation of all the possible connections that can be made from any place to any other place, because you have a connection between any place and any other place right here. And so it allows you to have a more robust, rich representation of what your distribution center actually looks like. Okay? And we're actually going to take advantage of this for our upcoming examples here. Okay? We're going to represent it to look like this kind of 2D grid where all possible connections we're going to consider from the mathematical model, and we'll just specially weight the non-existent conditions to be highly priced so that we won't actually use those, and we'll do the actual conditions with these low-valued prices right here. All right? Questions about that? Okay, so let's review the homework assignment for today before we jump into that. So that was, what, 620 was today's assignment? And I've already been told that this was another one of the problems that didn't line up between the newest editions and the older editions. I'm sorry about that. I will try to figure out the best way going forward. The scary thing is, I stopped looking after I got to chapter 5. It's like, oh, well, if the first 5 chapters are all the same, then of course the remaining chapters will be the same. And guess what? Chapter 6 is where they deviated. Yeah, so
I think it's just the 14th and 15th edition
that are different.
Yeah. So if you have the 14th
Right.
and 15th.
I do not have the 14th or 15th edition myself, but I was able to look at, Amazon, look at the contents without buying. All right, so I'm going to be going with the older editions here because that's what I have a copy of, and I'm sorry for those of you in the newer editions. All right, so we've got this situation here, right, where we've got these railroad cars, and we're trying to figure out where they should be distributed, right? And something that may have been confusing is that the prices are per bushel, but they never say how many bushels are in a railroad car, right?
Yeah.
So what you can assume for this problem is that all the cars have the same number of bushels in that they're all the same size, they're all full, and just count that price as the unit price for the car as large. Hopefully that's what you ended up doing. But that could be something confusing because there are more than one bushel in a railroad car, right? So we have these shipping costs, and we're going to go from, let's see, Muncie, and that is Muncie, Indiana, Brazil, and Xenia. So this is very local, right? And we can go to Louisville or if I can spell Cincinnati, right? And our amounts. We can just copy those. Okay, so that's from our supply to our distribution center. And let me make this a little bit bigger here. And then we have the same, whoops. Thing, let's do it. So what goes here in our model? The supply. And how much is shipped? And what goes, and this is received, right? I'm going to just go this a little bit here. Keep a little space in here. So this is inflow, right? So how much does Muncie have available? How much does Muncie have? 3. No, this is, how much does Brazil have? And how much does Xenia have? All right. And how do we compute how much gets shipped out of Muncie? Sum of what? How much we send to each of these intermediate spots, right? And we do the same thing with Brazil and Xenia, right? We compute those rows. How much comes into Louisville? It's the sum of what? It's that column, right? How much we send from each of those different places. And the same is true for Cincinnati, right? Whatever we send from Muncie, Brazil, and Xenia is how much gets. So now we do our costs here. How much does it cost to send from Muncie to Louisville? 8. And Muncie to Cincinnati? Brazil to Louisville?
3.
And
9.
okay, so we can do our shipping costs. So far, what is our shipping cost? How do we compute our shipping cost so far? Of what? Of how much it costs with how much we send, right? You know what? I labeled that wrong. This there we go. This is the amount we're shipping. This is how much it costs. Right? Okay. Oh, that's nice. So then, once we get it shipped to Louisville or Cincinnati, those are our starting locations, right? And where are our final destinations? Macon, Georgia, Greenwood, South Carolina, Concord, South Carolina, and Chatham, North Carolina. All right, let's just make that nice and readable. All right, and what goes here? Again, it's how much is shipped. Right? Or this is outflow, right? And down here is demand versus receipt. Right? So how much comes out of Louisville? Again, that's our sum of this row right here, right? Everything that Louisville sends to all those other. And the same is true for Cincinnati. We just take each row and sum them up. How much does Macon, Georgia want? 2. How much does Greenwood want? 4, 3, and 3, right? But how much does it receive? The sum of the column this time, right? Whoops. And the same is true for the other 4 cities as well, right? Bless you. So how does that cost? We need to do the same thing here, right? Louisville, Cincinnati, and I'm just going to copy that. Okay, so how much does it cost to go from Louisville to Macon? And then Greenwood?
34, 34, 32, 57, 35, 28, 24.
All right. And now, how does that affect our total shipping costs? What do we have to do? We need to add that second sum product, right? Which is between these values and these values here. All right. Let's go ahead and enter this into the model then. What's our objective cell? Shipping costs, and what do we want to do? Minimize. Okay, our variable cells. That is these. How much we ship out of Muncie, Brazil, and Xenia, along with that's going to be a problem. Let's try that again. All right. As well as how much gets shipped out of Louisville and Cincinnati, right? Those are the values that are variables. Now our constraints. We basically have the same three constraints, right? Our demand constraints. What are our demand constraints? It's that these right here, these values right here, are equal to what we actually received, right? Wait, did I do the same too? That's a problem. There we go. Those are our demand constraints, right? What are our shipping constraints? It's what we shipped is equal to what we supplied, right? That's wrong. What's wrong about that? What's wrong about? They don't add up. Right? How much do we have here? 11 plus 3 is 14, right? We have 14 cars. We have 6, 9, 12. Okay? So our supply is larger than our demand. Right? So how are we going to change this? It's not going to be an equality constraint. We can't do it. We can't ship everything out and have it all land here at the same, right? So since we have too much, where should the extra be in the end? Think about it logically. Should we ship any of our extra stuff? No, that's just wasted cost, right? So this should not be an equality constraint. This should be a less than or equal constraint because we don't have to ship everything out. It's okay if, for instance, we only ship 1 from Muncie and leave 2 behind. Or we ship 2 from Muncie and 5 from Brazil and leave 1 behind at each of these places. We know, just by counting here and counting here, that we have 2 extra. So there's going to be 2 extras left behind somewhere. Okay, so this is not an equality constraint. It's a less than or equal constraint. Okay, so we have our demand constraint, our supply constraint. What's our third type of constraint?
The inflow outflow constraint.
Yeah, that the inflow is equal to our outflow. So let's get that. Our inflow, we already said, is right here, right? And our outflow is over here. Whoa. So those are our 3 constraints. We have our demand constraints, our supply constraints, and our no net aggregation. Let's go ahead and solve this. And what do you know? We do leave 2 behind in Muncie. Okay, we only ship 1, we leave 2 behind. Wait for some other buyer to come and then ship it to that final location. All right, questions about this? Hopefully you're starting to get the hang of these transportation and transshipment problems. Once you get it, I think it's safe to say that it's pretty straightforward. It's just putting the right equations in the right places. All right? So let's start thinking about a new type of problem that we're going to couch in terms of a transportation problem here. Okay? And that is what's called a shortest path problem. Those of you computer science students have probably learned other algorithms for doing this, like Prim or Kruskal's algorithm. Okay, this is the same sort of idea here. We're going to have nodes and edges, just like we did with transportation. And so we can represent this as a transportation solution. Just to use a already made up model here, let's pick from the newest textbook, problem 624. We'll pick that graph that we have right here. So I'm going to write it on the board because I know not all of you have this textbook here. All right, and so can someone turn on the lights for me, please? It's hard to read, hopefully. It's better. All right, so I'm going to number this 1, 2, 3, 4, 5, and 6. And we've got now here, instead of these being costs, that it costs us to ship some product along this line, these represent distances, so that might be miles. Okay? This is the kind of thing that when you run your GPS unit and you say, how do I get from where I am to where I want to go? This is the exact same thing that it's going to do. Well, what's the shortest distance, maybe? Or maybe what's the shortest time that it takes to get from where you are to where you want to go? This is the exact kind of computation that needs to take place on these units to be able to give you the driving directions. And each one of these links right here represents a possible route. And each of these nodes is an intersection where you could turn left or right or go straight, whatever the case may be here. So, so these get used obviously all the time by us as we're driving. Right here. All right. So this is a location. Say this is Taylor University, and let's say this is the Indianapolis Airport. Try to get me there as fast as possible. And these are the different places where I can make turning directions. Obviously, there's more than 6 total stops along the way between those two. But this, again, is a simplified version of the same thing. Okay. Now, notice here that I have what are called undirected edges. In other words, I can travel between location 1 and location 2 in either direction. I can go from 1 to 2, but that also means I can go from 2 to 1. Okay. I can go from 2 to 4, or I can go from 4 to 2. Okay. So let's just say right here 1 is going to be our starting location, and 5 is going to be our destination. 6, thank you, is our destination right here. Okay. Well, it turns out that we're going to slightly augment this graph a little bit. We know we should always be leaving our starting location. We should never get back to it. So even though these are bidirectional links from our starting location, we know we're only ever going to want to go this direction. We're not going to want to end back here, because if we did, that's going to be problematic, right? We should have just gone some other way to begin with. So we're only going to put the outbound routes from our starting location. Similarly, we're going to only put our entering directions to our final destination, because once we're there, we don't want to turn around and leave. We're there, we've met our destination. But at all other links on our graph, we don't know where we're going to arrive first, and whether, let's say from 3 to 2. We don't know if we should go from 1 to 2 to 3, or if we should go from 1 to 3 to 2. We need to make both of those routes available to us because we don't know which one, if either, we should take in our final travel. So we're actually going to put an arrow here and make another link here, just like that. Okay? And we will do the same for all of these links right here. Because we don't know a priori which link we're going to take. The only ones we absolutely did know were out of the start and into our destination. So we only had to do one way for that. Did I catch them all? All right. So here's what we're going to do. We're going to pretend like we've got a product that we have available here, and that the demand for that product exists over here. And now we've turned this into a transshipment problem where we need to get this product from here all the way over to here. Okay? So let's go through our 3 rules real quick. What's the rule right here for the starting? Does this look like, what kind of rule does it look like? What does the start node look like to you if you compare it to a transshipment? It looks like supply, right? We've got this product that we want to get out of here, right? So what do we want to have happen? We want to get that one out of here, right? So x12 plus x13 better equal 1, right? That's our supply. What's our demand constraint going to look like? Where does the demand exist? Which node? 6. So what should be true about 6?
2, 6 plus 4, 6 plus 5, 6 equals 1.
Okay, which leaves our no net flow, or no net aggregation, let's be clear, or our types of rules left. So at 2, what do we want to be true? We want our in to be equal to our out, right? That's what this means. What is coming in to node 2?
1, 2, 3, 4.
Okay, and what's going out? 2 to 3, right? 2 to 4, and 2 to 6. Right? We could go that link, or that link. How about node 3? What do we want to be true there? 1, 3 plus 2, 3 plus 5, 3. That's everything that comes in. What's everything that goes out? 3, 2, 3, 5. Right? And we can repeat this for node 4 and node 5. And in general, we would do this for every single node here, right? So we got one supply node, we have one demand node, and all the rest look like this: in equals out, right here. Right? So let's see if we can at least set this up before we run out of time. All right, so I'm just going to do 1, 2, 3, 4, 5, 6 because we don't have fancy names for them in this graph. 2, 3, 4, 5, 6. Okay, and I am going to copy this down here. And this is going to be the distance. And this is the travel. And I'll put a question mark there. Okay? And now we're going to do what we talked about earlier in the day. What's the distance between node 1 and node 1? Is there a connection between node 1 and its No, so we're going to put 1,000 in here, right? What's the distance between node 1 and node 2? 40, okay? What's the distance between node 1 and node 3? How about 1 and 4? There is no connection, right? 1 and 5? And 1, 6. And then we keep doing this. 2. Does 2 go to 1? No. So we have 1,000 here. Does 2 go to itself? So we have 1,000 again. Does 2 go to 3? At what distance? 6, you said? All right, how about 2 to 4? 12? 2 to 5? And 2 to 6? Thank you. How about 3? Does 3 go to 1? How about to 2? To itself? To 4? To 5? And to 6? All right, how about 4? Does 4 go to 1? Does 4 go to 2? All right, how about 4 go to 3? 4 go to 4 itself? 4 go to 5? 8, you said? And 4 go to 6. How about 5? Does 5 go to 1? 5 go to 2? 3? 5 to 4? 5 to itself? And 5 to 6?
5, 3 is not 1.
15? Thank you. And then 5, 6. The 6. Right? There's nothing coming out of 6, right? Okay. So now this right here, this part of the graph is are the variables, right? And we can compute the total distance traveled. Whoops. By doing what? The sum product of the distance between a node and whether or not we're going to travel between any of those nodes, right? So, let's think carefully. What does this row represent? What does this row in this table represent? Going from 1 to any of these ones. What does this column represent? Going to 1, right? Okay. So we know, for instance, here, this row right here, what do we want to be true about this row? How much should be leaving row 1? All of it, which is 1 in this case, right? How about row 2? How much should be leaving row 2? Huh? Whatever came into row 2. Where is that? It's this column right here, right? How about 3? This is everything that leaves 3, right? And what is it? What should it equal? Everything that came into 3, right? Which is this column right here. And we can keep going, right? What is this? This is everything that leaves 4. And it better be everything that comes into 4. And we can do that for 5. This is everything that comes into 5, right? Or actually, that's everything that leaves 5. And it better be equal to everything that comes into 5. Now here, this is everything that leaves 6, but we don't want that, right? What we want is we're going to put a 1 here, right? Because we want that to be everything that comes into 6 right here. Right? And so I know we're past time, but this is super easy, right? Our objective cell is that we want to minimize our total distance traveled by modifying these cells right here such that this column equals this column right here. What's that? And quickly we can say we go from 1 to 2, from 2 to 4, from 4 to 6 is the shortest path through that path right there. All right. I'll see you guys on Wednesday.